Hey everyone, Isaac here. In this video, we're going to go through what you need to know about the Haar measure to use it in the context of variational quantum algorithms. Now, what's got a bunch of unitaries in it? Quantum circuits. And why would we need them to be random unitaries? Well, to initialize a quantum circuit in some random state. That's when and why you would need the Haar measure, to randomly initialize a quantum circuit as the first step in any good variational quantum algorithm. Before we answer what is the Haar measure, it's important to understand what a measure is in the first place. A measure provides a description for how things are distributed in a mathematical set or space. If you're coming from a background in physical sciences, math, or computer science, odds are you've already seen measures in action in these scenarios. When integrating a function in spherical coordinates, say, the measure is the differential on the screen, which tells us how an infinitesimal chunk of volume is distributed in spherical coordinates. You've probably been exposed to measures when you want to sample from a probability distribution. For the physics students, you've probably seen the Gibbs measure, which is a probability distribution in statistical mechanics. But hey, if you've ever done any of those things, you already have some exposure to measure theory. Now, what is the Haar measure and how do we use it? Again, a measure is just a description for how things are distributed in a mathematical set or space. And the Haar measure is a description for how n by n unitaries are mathematically distributed. In other words, if we want to integrate a function over n by n unitaries or sample random n by n unitaries, we'd need the Haar measure. Now begs the question, what is the Haar measure? Show me the math. We encourage you to go check out our demo on the PennyLane website, which we have linked down below. There's also some papers that we have there as well. Check them out if you're really interested in getting into the math. Here we'll go through a nice result from this paper, which basically shows us how to generate Haar-random unitaries. The steps you need to take in order to generate an n by n Haar-random unitary are actually quite straightforward. The first step is to generate an n by n complex matrix, which we'll call Z. Its entries are going to be of the form A plus IB, where A and B are random numbers drawn from a normal distribution with a mean of 0 and a variance of 1. The next step is to compute the QR decomposition of Z. Doing the QR decomposition of a matrix will give an orthogonal matrix that we'll call Q and a triangular matrix called R. If you're unfamiliar with what the QR decomposition is, we have a link in the description for that. The next step is to compute a matrix that we'll call capital lambda. Its entries are calculated from the triangular matrix R that we calculated in the QR decomposition, and it's a diagonal matrix. Its entries are basically the diagonal entries of R scaled by their magnitude. And the final step is to compute this matrix Q prime equals Q times capital lambda. And Q prime will be Haar-random. I encourage you, if you're interested, to check out our demo and the paper from which this algorithm stems from to understand why it works. Okay, so let's code up that 4-step algorithm that will generate a Haar-random unitary. And then what we'll do is we'll plug that into a quantum circuit and optimize it a few times just to show that in principle you could do this for any variational quantum algorithm that you want to set up. So of course we're going to do everything in PennyLane, and we'll for sure need NumPy here as well. NumPy has a lot of linear algebra functions, specifically a function that will compute QR decompositions for us, and we'll use that in this algorithm that will generate Haar-random unitaries. And that NumPy linear algebra function is called QR. It does QR decompositions. Let's define a function that does this 4-step process to generate n by n Haar-random unitaries. Step number 1 says to generate a matrix Z whose entries are complex, and the real and imaginary parts of those complex numbers are randomly sampled from a normal distribution with a mean of 0 and variance of 1. So what I'll do is I'll create 2 random matrices, A and B, and I'll use those to define what Z is in a second. But the elements of A and B just need to be sampled from that normal distribution randomly. So we can use NumPy's random.normal function for that. And then we can define the matrix Z, which is just A plus IB. Okay, so that's step number 1. Step number 2 is just to do the QR decomposition of Z. And here we can just make use of NumPy's QR function that we imported above. The second last step is to create this matrix lambda, and it's a diagonal matrix, and its elements are the diagonal entries of the matrix R that we computed from the QR decomposition, scaled by their magnitude. And finally, to get a Haar-random matrix, we just need to multiply the matrix lambda with Q. And that's it. All right, so now that we have a method for creating n by n Haar-random unitaries, let's actually use this in a quantum circuit. Now, if we just wanted to stick a Haar-random unitary using the function that we just created into a quantum circuit in PennyLane, we could just use qml.qubitUnitary. Basically, that operation takes in a unitary matrix and plunks it into a quantum circuit. But what we want to do is do some optimization steps on the circuit. And we have to be really careful here. If we want to optimize the entries in the unitary matrix we created using, say, a gradient descent update rule, we're not going to end up with a unitary matrix after one step. Instead of optimizing the entries of a unitary matrix, we can decompose that unitary matrix into, say, a set of rotations, where now we're instead optimizing the angles of the rotations. And there we don't have to worry about numerical optimization destroying the unitary property of the operation. In short, what we need to do instead is take our Haar-random unitary and translate it into parameterized rotations. So let's calculate a Haar-random matrix using our function we made. And note here, capital N is 2, meaning that we'll generate a 2 by 2 matrix, which is the proper dimensions for a 1-qubit operation. So luckily in PennyLane, there are functions that take a unitary matrix and translate them into parameterized rotations. One of those functions is called ZYZ decomposition. So this function, as a first argument, takes the matrix. Second argument is the wires that it acts on, which in our case is just the 0th wire. Okay, now let's just print out what this operator is. And as you can see, it spits out a one-element list where the element is a qml.rote operator. It is parameterized by 3 angles. So this is the operator that we'll put in our quantum circuit instead of qml.qubitUnitary. And just before we go ahead and create a quantum circuit with that rotation gate in it, and that's it, just need to grab the parameters of the operation so that I can feed it into my quantum circuit and differentiate with respect to them. Parameterized operations in PennyLane have a parameters attribute that just spits out the parameters of the operation. The variable op that we created up here is actually a list containing an operator, so I just need to access the first element of it, and then I can call parameters. And finally, I just need to make sure that PennyLane knows to differentiate with respect to these parameters. There are 3 parameters that define the angles of rotation in the qml.rote operator, and then I'm just sticking them into a numpy array and saying requires grad equals true. And finally, I can create my 1-qubit circuit with the qml.rote operator, just noting that the qml.rote operator requires each angle individually as an argument, so I'm just feeding in an unpacked version of the parameters that I feed my circuit. And let's just say we want to measure the expectation value of the polyx operator. And now we just do the optimization where I've initialized the qml.rote operation as a Haar-random unitary, and it works. The benefit to using the Haar measure as a way to initialize your quantum circuit is that it gives you a quantum state in the Hilbert space uniformly at random. In other words, the circuit ansatz spans the entire Hilbert space, meaning that you're guaranteed that your quantum circuit represents the state that you're after, which could, for example, be, like in a VQE procedure, the ground state of a Hamiltonian. So why don't you see Haar-random circuits more in research when they're relatively easy to generate and they're highly expressive? Well, it turns out that initializing circuits in this way leads to barren plateaus, which are regions in parameter space that are extremely flat, making optimizing your quantum circuit very hard. To wrap things up, you really need the Haar measure when you want to sample random unitaries or average functions over unitaries. Therefore, from a theoretical point of view in research, the Haar measure is paramount. That's all for today's video. If you liked it, be sure to give us a thumbs up. Put any questions or comments that you have down below in the comments section, and subscribe to our channel for more quantum programming content from Xanadu.